Пожалуйста, вы можете проверить, есть ли звук со своего рабочего места? Можете проверить? Ага.
Good afternoon, everybody. Let me greet the International Medical Faculty first year students of the third division. Today we start the option of lectures on this discipline. You start to learn now medical and biological physics. It is lecture number 1, mechanics, general basics, biomechanics, some aspects. Actually, you get 8 lectures. Sometimes they will ahead, sometimes behind your tutorials. Nevertheless, this option aim is to support your learning on this discipline as medical and biological physics. Let me introduce, I'm Associate Professor Natalia Pronina. I'm lecturer for your division. And now let's start the first lecture. What is the goal for us? The goal is to quantify human musculoskeletal system mechanical performance, and we will base upon mechanics concept. So actually, from the very beginning, let me pay your attention to the distinguishing feature of this discipline as medical and biological physics. Physics, actually, it is the fundamental science, and the distinguishing feature of this science is to quantify the properties, the processes of the nature taking place into our surrounding. And this provides the ability to speaker not to say by words that are dependent on speaker about surrounding world, but to say concretely, to determine absolutely strongly the properties of the objects and their behaviors. But we don't deal, and it is not the task for us to look around us and to describe, to consider the process into the nature surrounding us. We take physics, we use physics as the opportunity, as the tool to describe, to look inside the human's body and to quantify such complicated processes as physiological processes, as biological processes, in addition to that other discipline you are learning now. So that is why the goal will be repeated from lecture to lecture. We'll bring this goal through the whole course of the lectures, the quantification of human structures, functions and properties. Particularly today, the goal is to quantify the human musculoskeletal system mechanical performance, and will base upon mechanics concept. Objectives: mechanics parameters, nomenclature, and basic laws review. This is number 1. And then mechanics modeling of human musculoskeletal system structures. This is the list of the This is the list of the question we will go through. First of all, let's look inside the mechanics and let's recognize mechanics basic aspects. Then mechanics specification of skeletal muscle contraction. We look on this function of skeletal muscle from the physics point of view, and skeletal muscle functional state may be diagnosed by dynamometry method. Let me introduce you that method. And after that, we take these two structures that are in relation, that are in interaction with one another. These are musculoskeletal and structures working together and developing this mechanism as levers. So let's start. Introduction, mechanics, basics, aspects. Any physical phenomenon or process in the world around is a natural series of changes taking place in time and space, and mechanical motion is no different. Actually, it is the change of a body or its parts, positions in the space relative to other bodies. Mechanical motion is studied in the physics section, that is mechanics. The main task of mechanics is to determine the position of a body into the space at any time instant. So, and to determine, let me stress one more time, it is not to describe, but to determine. And you may know that the equation of the motion may be written down in an analytical form, and this formula may be used to calculate and strongly determine the position of the body into the space at any instant, at any moment, and relatively to other bodies. Mechanics involves such kinds of investigations. When you want to know how does the body move, it is the subject for kinematics. When the reason of the motion is of your interest, you should go through the dynamics. Dynamics considering the action of some bodies on another as the cause of movement and answering just to that question. Why does the body move this way and not otherwise? And finally, statics. It is the study of the forces acting on an object that is maintained at equilibrium or at rest. So, mechanics, it is the study of the mechanical processes from different point of views. I can say so. Okay, quantitative discussions of motion are based on measurements and calculations of positions, displacements, velocities, and accelerations. This is just the nomenclature of the terms of the mechanics. Positions, this means the set of the coordinates showing the position of the body under investigation into the space relatively other bodies. Displacements, this is the change of the position, and this change may be quantified as well. Velocities and accelerations. These two more parameters may be calculated or measured, and these are the parameters quantifying the mechanical motion process. This simple example for the introducing these concepts is translational motion, a long straight line. in which every part of an object moves in the same direction and there is no rotation. The velocities and accelerations of all points of a body at translational motion at a given time are the same. So it is reasonable to take the only one point at the body and consider only this point direction, supposing that the all mass is concentrated just at this point. For example, this might be center of the mass of the body. This allows the study to make study easier, and this is just the simplest case of mechanical motion. In rotational motion, about an axis, each body point is undergoing circular motion. The body, all points, circular paths, centers are at the rotation axis, as in this particular case. You can see these circular paths are of different radii. The centers of these circular paths are at the line crossing, going through the body. It is the rotation axis. And when we talk about the ability of the force to rotate the body, we prescribe the force one more quantitative parameter. It is the force torque. It is enough to talk about the only force when we consider the translational motion. But rotational motion is different, and this one more characteristic as the torque of the force is required. The torque depends on the force, the distance from a point on the axis of rotation to the point where the force acts on the object, and the angle between these two lines. This is illustrated here, and the formula to calculate this force characteristic is given as this analytical equation. So, look, when we talk about rotational motion, this ability of the force to cause this motion depends on the point where the force is applied to the object. As for translational, it is no such relation. The direction of a torque is given by the right-hand rule and indicates the axis about which rotation will tend to occur. Using the right-hand rule, we point the fingers of our right hand in the R direction. When our palm faces the force, our thumb shows the torque direction. We can rotate our fingers 90 degrees toward the force, determining the direction of an object rotation. So, and let's come back to the translational motion. An object is set into motion when it is pushed or pulled or subjected to a force. And this force should be considered as the resultant total force that is developed by several might be objects that are subjecting the object of the interest. Forces have both magnitudes and directions, so they are vector quantities. So, and it is found that the net or total force on an object is the vector sum of the forces acting on the object. Newton's three laws of motion are fundamental statements about the physical world. Newton's first law of motion is of two statements. When there is no net force, the total resultant force equals to zero. An object under investigation is at rest. And second statement of the Newton's first law, an object in motion continues to move with a velocity that is constant in magnitude and direction at the same condition when there is no net force. The second law of motion, the force needed to produce an acceleration equals the product of the mass and acceleration. So one more time, let me pay your attention that it is not the concrete force. This should be considered as the resultant total force on an object that are set into the motion with the acceleration. And finally, Newton's third law of motion. If one object exerts a force on a second, then the second object exerts an equal but opposite force on the first. So, and what about statics? It is the study of the forces acting on an object that is in equilibrium or at rest. Our discussion of statics is based on an idealized object, the rigid body, an object extended in space that doesn't change its size or shape when subjected to a force. Objects such as human bones are often rigid enough to so that their deformations and at standard conditions of motion are negligibly small. So you can see one more physics model to consider the mechanical behavior of the objects, rigid body. It is physics model when we simplify the situation, meaning that we don't take in account the deformation of the body under forces applied. So a rigid body will be in equilibrium if two conditions are satisfied. The condition that the net force is zero. For a rigid body, this condition means that the body as the whole are not accelerated, or it is in translational equilibrium. And to provide the equilibrium state of the rigid body, the second condition should be satisfied as well, the absence of a net torque. It is the second condition necessary for the equilibrium of a rigid body. So, and now let's look at this rigid body that may be in this condition. And what is that condition? You can see that rigid body is supported, and around this point of support or axis that is crossing this point of support around this axis or the point this rigid body can rotate. And such a combination of the rigid body, of the point of the support of that rigid body and forces that are applied to it. This is considered as the lever that is the simplest mechanism. That is the simplest mechanism. A lever in its simplest form is a rigid bar used with the fulcrum. Fulcrum, that is the point or axis of rotation. Levers are grouped into 3 classes depending on the relative placement of the fulcrum, force applied, and load or resistance. A lever is an example of machines. In this case, a force is applied and load is balanced. The class 1 levers have a central fulcrum with a force F applied on one side and the load on the other. The first class lever. For the class 2 levers, the load is central and the force F and fulcrum are on other sides. It is the class 2 levers. For the third levers class, the force is applied centrally and the fulcrum and load are on opposing ends of the arm. The mechanical advantage of the machine is defined as the ratio of the magnitudes of forces F and load. And let's stop with the mechanics basics and let's look inside the human's body and let's find that mechanics inside the human body. Maybe it is not reasonable to talk about mechanics because there is no such as mechanical processes inside us. No, there are such processes and look, these are examples of that mechanics maybe found into the human's body. Skeletal muscles contracting and relaxing perform translational motion. This is the example of translational motion. Skeletal muscles exert mechanical forces. Skeleton bones are rotating under muscles' forces. External and these two should be considered as the mechanical motions that are taking place, that are functions of the structures of the human body. And one more should be mentioned. External and internal forces act on human body, causing structures deformations. Deformations of different types reveal the mechanical properties of tissues. So you can see much enough mechanics can be found inside the human's body. So, and it is actual to look at these human body mechanics from the physics point of view. And let's consider, first of all, I determine this as an active structure that initiates, that results mechanical process as mechanical motion into the human body. It is just the main function of that structure. This is the skeletal muscle. Skeletal muscle, as any tissue, is composed of multinucleated skeletal muscle cells that are very specific. First of all, as I said already, these are multinucleated. These cells include not the only one nucleus, but several. Because this cell was developed by several cells, and this gives this composition of the skeletal muscle cell involving several nuclei. One more, the skeletal muscle cell looks, or it is, the fiber in its structure and shape, running from one end of the muscle to another. These fibers vary from approximately 10 to 100 micrometer in diameter and can be several centimeters in length. Depends on the size of the particular concrete skeletal muscle. The skeletal muscle fibers are not single, are not separated from one another. Instead, they are grouped into fascicles of approximately 20 fibers, and this is done by perimysium, a connective tissue sheath that is continuous with the connective tissue surrounding the entire muscle. The perimysium is continuous with the endomysium surrounding each muscle fiber. The endomysium is continuous with the sarcolemma, a sheath that contains glycoprotein and closely envelops the true cell membrane of the muscle fiber. The tight connection, look, this, the tight connection, sarcolemma, endomysium, perimysium, epimysium, and after that tendon, periosteum, and then to bone. This tight connection between the cell membranes and surrounding connective tissue and then with the bone structures enables the force developed by each muscle fiber to be transmitted effectively. First of all, these single elementary forces of all fibers are gathered, and after that they are effectively transmitted to the tendons. So let's come back a little to the previous and recognize more detailed the structure of the skeletal muscle fiber, single skeletal muscle fiber. The individual skeletal muscle fiber are divided into myofibrils by a tubular network called sarcoplasmic reticulum. The myofibrils are approximately 1 micrometer in diameter and extend from one end of the muscle fiber to the other. The myofibrils, in turn, are divided into functional units or sarcomeres by a transverse sheet of alpha-actinin protein called the Z-line. You can see this functional unit or sarcomere. And this alpha-actinin protein sheet, the Z-line. The myofibrils are not elementary fibers in its structures, but the myofibrils contain thick and thin filaments composed of contractile proteins. Thick filaments contain the protein myosin and are approximately 11 nanometer in diameter and 1.6 micrometer in length. Projections from the thick filaments, called cross bridges, extend toward the thin filaments. You can see these projections that run into the space between thick and thin filament. Cross bridges play a fundamental role in muscle contraction. Thin filaments, you can see, these are strongly attached to the Z lines. They contain three kinds of the proteins: actin, tropomyosin, and troponin, and are approximately 5 nanometer in diameter and 1 micrometer in length. You can see that diameter is much less than 11 nanometer diameter of the thick filament. So that is why these two, based on their diameters, are separated, classified, determined as thin and thick filaments. So, and what else should be mentioned about the structure? The tight connection between the cell membranes and surrounding connective tissue structures enables the force developed by the muscle fibers to be transmitted effectively to the tendons. One more time, let me stress you the specificity of the arrangement of the skeletal muscle. One more time, let me illustrate these thick filaments that contain the protein myosin, projection, thin filaments containing actin, tropomyosin, and troponin. You can see this as Z line. Thin filament are attached strongly to the Z line, and this fragment between two adjacent Z lines, it is the functional unit of the myofibril sarcomere. And you can see one more specificity of the position of the thick and thin filaments. They are strongly parallel to one another, and they are directed along the myofibril. In turn, the myofibril is running along the muscle fiber, and all muscle fibers are running along the skeletal muscle, and this order can't be destroyed for the normal function in case of the normal functional state of the skeletal muscle. Two tubular networks are present in skeletal muscle fibers. The transverse, it is named as the T-tubular network. Transverse T-tubular network, you can see what it is here, is formed as an invagination of the invagination. You can see that invagination of the surface of the muscle membrane. Action potential spreading over the surface of the muscle membrane is propagated into the network of the T-tubules. this is the invagination, this the ending of the nerve cell, it is the ending axon, and action potential from the axon is transmitted to the T-tube, and these T-tubules form specialized contact with the one more tubular network that is longitudinal sarcoplasmic reticulum. The internal tubular structure that runs between the myofibrils. Let's look at it. Sarcoplasmic reticulum. You can see this reservoir that are filled with the solution of the calcium high concentration T-tubular network perpendicular to the muscle fiber and longitudinal that is running through the myofibrils. And the action potential, nerve impulse, goes transmitted to the T-tubular network membrane, and this is the signal for the sarcoplasmic reticulum to open the calcium channel and to release the calcium into cytoplasm of the skeletal muscle fiber. The sarcoplasmic reticulum has a high concentration of calcium, which is used to initiate muscle contraction when the muscle is stimulated. And now let's consider this excitation-contraction coupling. Excitation-contraction coupling is the process by which an action potential initiates the contractile process, the contraction of the muscle. Excitation-contraction coupling involves 4 steps. The propagation of an action potential into the T-tubule and release of calcium from the sarcoplasmic reticulum, and this starts the skeletal muscle contraction. The first step is the binding of the cross bridge to the actin. Binding occurs spontaneously after calcium binds to troponin. You can see at this concentration of the calcium, at the rest state of the skeletal muscle fiber, there is no binding between the cross bridge of the myosin filament and the actin that is at the thin filament. Because these places where these two, actin and myosin, can develop the connection with one another, are hidden by the tropomyosin. And what is the role of the calcium? Calcium, after its concentration becomes greater than 0.1 micromole per liter, opens, calcium binds to troponin, it will be better to say, and this change the configuration of the thin filament And you can see these myosin binding sites on the actin become open, and myosin binds to the actin. The activated muscle proteins undergo repeated cross-bridge cycling, during which the muscle uses the energy obtained from the hydrolysis of ATP to shorten and generate tension. The cross-bridge cycle can be divided into 4 steps. The first step is the binding of the cross-bridge to actin, as described. Binding occurs spontaneously after calcium binds to troponin. The second step is the bending of the cross bridge, which pulls the thin filament over the thick filament, generating tension. The energy used to bend the cross bridge is generated when ATP is hydrolyzed. Both the ATP molecule and the ATPase required for its hydrolysis are located on the cross bridge. However, ATPase is activated only when myosin binds to actin. Therefore, hydrolysis occurs only during cross-bridge cycle. The third step is the detachment of the cross bridge from the thin filament. This occurs after the cross bridge has bent. And after that, we can say about the fourth step. The cross bridge returns to its original upright position. Once there, it can participate in another cycle. Cycling continues as long as calcium is bound to troponin. Relaxation of muscle occurs when the calcium is removed from the cytoplasm by calcium pumps located on the sarcoplasmic reticulum membrane. When the intracellular calcium concentration falls below 0.1 micrometer per liter, troponin returns to its original conformational state. Tropomyosin inhibition of myosin-actin interaction is restored, and cross-bridge cycling stops. So you can see this process of energy transformation. What is that? The chemical energy of the ATP molecule is converted into mechanical motion of the cross bridge. It bends and pulls the actin filament toward the center of the sarcomere, and this is just the shortening of the sarcomere and consequently the shortening of the skeletal muscle. Let me pay your attention and one more time to stress that this parallel structure, parallel placement of the actin and myosin can't be destroyed. So look, skeleton having muscles fiber is analogous to optical fiber in electronics industries used for communication. Look, I don't agree at all with this statement. It is not so, actually. We talk now about the term that is used here in physiology particularly, but it is not analogous to optical fiber. It is absolutely different, so it is not quite correct to compare these two. And look, let's consider shortening and force development. It is produced by the sliding of thin filaments over thick filaments. The contractile properties of muscle can be studied into two types of mechanical conditions: isometric and isotonic contractions. The thin filaments are drawn to the center of the sarcomere by the repetitive cycling of cross bridge. Each time an attached cross bridge bends, it generates a force that pulls the Z line toward the center of the sarcomere, as I said already. The force developed by the bending of the cross bridge is transmitted through the thin filament to the Z line and then through the sarcolemma and tendons insertions of the muscle to the bones. So we can say, and this should be mentioned. Neuron as a unit cell of nervous system of organ. Yes, I agree with this statement, and the ending of the neuron is in contact with the skeletal muscle, and it brings electrical, as you name it, nerve impulse to the skeletal muscle fiber, initiating the release of calcium from sarcoplasmic reticulum. And when concentration of the calcium becomes greater than 0.1 micromole per liter, the interaction between thick and thin filament is allowed. And after that, you can say about the 4 steps of the contraction of the skeletal muscle, particularly of the contraction of the sarcomere. So, and the next should be mentioned one more time. Shortening and force development is produced by the sliding of thin filament over thick filament. And look, isometric contraction, the type of skeletal muscular contraction in which the force applied by the muscle is not sufficient to move the load, and as a result the muscle doesn't shorten through its muscle tension, though its muscle tension or force of contraction increases. This is just the illustration of this. Isometric contraction. The resulting force development is the muscle twitch. After the only one nerve impulse is stimulated by the single nerve impulse, what we can see? We can see here the change of the concentration of the calcium with time, and this leads to the muscle contraction, single contraction, that is named as the muscle twitch. And you can see it is delayed a little. It is understandable that the time small but short, but time is required to develop this linkage between myosin and actin proteins. If the frequency of stimulation is rapid, individual twitches become one continuous contraction. That is, a maximum force is generated. The frequency required to produce a maximal force is called a tetanic frequency, and the resulting contraction is called tetanus. You can see the stimulations that follow one another with particular frequency and don't stop lead this set of the stimuli leads to the change of the calcium following the same frequency, and consequently to this the contraction looks like these not completed twitches. So, and this is just the tetanic, tetanus character of the contraction. And you can see that the force developed in this case is greater than the force that is twice greater at least than the force developed within one twitch. The length tension relation. Length means or is prescribed to the length of the sarcomere. You can see that the length of the sarcomere may be changed, it may decrease, it may increase, and in both cases you can see that the overlap of the thick and thin filament in this case decreases. So that is why the less number of the linkages between the thick and thin filaments may be developed, and consequently less force is developed by the muscle. So the optimal length of the sarcomere when the force developed by the muscle is around these 100. What it might be. Unfortunately, there is no measuring unit. Okay, let's take this as percentage, sarcomere length, percentage, sarcomere length. So, and this is at normal state, 100% of the sarcomere length, the force is the maximum. The overlap between the thick and thin filaments determines the number of cross bridges that will bind to actin when the muscle is stimulated, and consequently the number of these linkage develop the more or less force of the skeletal muscle contraction. Okay. The contractile properties of muscle can be studied into two types of mechanical condition: isometric and isotonic contraction. Isotonic contraction, the type of skeletal muscular contraction in which the force applied by the muscle is sufficient to move the load, and as a result the muscle shortens while its muscle tension remains relatively constant. You can see this illustration of this kind of the skeletal muscle contraction as the isotonic tonic contraction. So the load is not too much for the muscle, and it can be kept and moved. So that is why muscle is moving when it is working lifting, for example, this external load. And look, this as isotonic contraction is that kind of the contraction of the forearm arms that may be investigated, and the force developed by the groups of the forearm arms may be measured, and this method is the hand grip strength test. It is the procedure of measurement of the maximum isometric strength of the hand and forearm muscle group. So hand grip strength is important for any sport in which the hands are used for catching, throwing, or lifting. Also, as a general rule, people with the strong hands tend to be strong elsewhere. So this test is often used as a general test of strength. So here you can see the forearm muscle groups that are under investigation by this hand grip strength test. Hand grip strength test is a procedure of measurement of the maximum isometric strength of the hand and forearm muscles group. You can see what is the hand grip dynamometer, how it looks like, and you can see the procedure to carry out this investigation. And after that, you can see that I said at the beginning. By that means you measure directly, independently on you, the parameter, the force developed by the muscles at the forearm, and this becomes to be the evidence information about the functional condition, functional state of the muscles groups of the muscles of the forearm. And after that you can compare the data obtained and do your decision about that state of that muscles. And this, repeat one more time, becomes to be absolutely objective, independent information, diagnostic information. Of the same means, by the same means, you can measure the trunk muscular endurance testing may be done with low back problems, have relative weaker extensor strength relative to their flexor strength, rather than actually having weaker muscles. So you can measure back muscles force developed by this, one more time, dynamometry. So, and this is the procedure, and one more time you obtain the quantitative characteristic of the functional state of the human body. And what else should be said about isotonic? The contraction is called isotonic because the force remains constant during the contraction. The velocity of shortening remains constant. The relationship between the load and velocity is called load-velocity relationship. The greatest velocity of shortening is generated when the load on the muscle is zero. The peak velocity of shortening is an indication of cross-bridge cycling speed. So you can see this relation between the force, that is the load, and the velocity of the skeletal muscle contraction to be under this load, and you can see that this relation is inversely proportional. The less load, the larger, the faster motion of the muscle. And at the absence of the load, the shortening of the muscle is the most fast. And now please let me suggest you one more example how physics works when you consider the processes, particularly as we consider now the skeletal muscle contraction. Look, it is very close to be true that muscle may be considered, can be considered as the cylindrical in its shape. And we can talk about the cylinder of the mass we marked by M capital, and muscle tissue is of density we mark by this symbol rho, and A is cross-section area of the thickest part of the skeletal muscle. L is denoting the length of the skeletal muscle, and after that you know this formula that the volume of the cylinder, not volume of the cylinder, but the volume of any object may be calculated as the mass over density. And when we talk about cylinder, this volume may be calculated as the cross-section area times the length of the cylinder. So these now, what do we do now? We develop the geometrical model of the skeletal muscle, and then look, this as the free end. For example, we can say so of the cylinder is under the force, and this may be considered as the force developed by the muscle when it contracts. So, and how we can consider this? We can consider this as the motion of the point under the force, at the same direction as the direction of the force. It is the simplest case of translational motion. So consequently, we can write down this formula for the work that is done by the force to move the object or material point. So, and this formula is just this force times the displacement of the body. So, and when we replace the force by that means, this becomes another analytical equation. And what is this? It is the product of the cross-sectional area of the skeletal muscle and this elementary force that is considered as the force developed by the skeletal muscle at its cross-section of a unit area. It is actually physiological constant for all skeletal muscles that are at normal condition. So, and this F is equals to 30 up to 40 newtons over centimeter squared. So it is the constant as well as this density of the skeletal muscle tissue. So after that, look, what is the displacement in this case? It is just the absolute shortening of the skeletal muscle. It is the change of its length. It is the difference between the initial length and the final length. So, and one more we need, it is the relative shortening. It is the ratio of the absolute shortening and the initial length. So, after we substitute this, look, let's time and divide this equation by initial length. And after that, we obtain this equation. And when we substitute these two constant, we mark by k, into this equation, we obtain this analytical formula. Look, now what is this? It is the evidence that the mechanical work is directly proportional to the mass and the relative shortening of the muscle. The greater mass of the skeletal muscle, the more work muscle can do. So, and the we can state this from back to the beginning. The greater work will be done by muscle from time to time regularly. The muscle mass becomes greater. It is growing. So the greater mass reveals the greater work done by this muscle. So, and after that, let's come back to this combination of the skeletal muscles and bones. These muscles are attached to. Movements of the human musculoskeletal system are accomplished by sets of bones, joints, and muscles that work together, much like liver system. So let's look one more time and recognize these three classes of the livers and compare these classes with the concrete with the concrete structures into the human's body. The skull may be considered as the first class liver. So, and two forces are applied to this rigid body. So, this we consider as the forearm. This is the liver as well of the third class. And look, the tensed muscles exert a force on the bone at the place where it is attached to the tendon. The bone muscle system acts as a lever with the joint as fulcrum. The muscle provides the effort that is marked by E, and the load may be weight of the part of the body being moved or may include an external load. You can see this external load. So, and the effort that is exerted by the biceps. And now look, this combination of the muscle, biceps and forearm may be modeled and illustrated by this diagram. Elbow joint shown here as the fulcrum. And it is true, it is correct to state that the forum may be considered as the rigid body that is rotated into the around the fulcrum. The forum is rotated into the elbow joint, and these forces are applied. The biceps force and at the center of the forum we have to say about gravitational force on the forum from the earth. And at the hand, a person can keep something of this weight, and hand is now the support for that load. So we have to include this force on the forum. And from the shoulder, you can see the force R is applied as well to the forearm at the point of the elbow joint. And now we can write down the equation to describe this posture of the forearm as the equilibrium position state of the lever developed by the forearm. And what are these two conditions for the lever to be at the equilibrium? The first condition to be at translational equilibrium is expressed by this. The geometrical sum of the force applied should be 0. So there is no net force on the lever. And this be expressed by that means. Then we should include one more. We should include one more. Okay. So this is just that translational equilibrium equation you can see. So, and it is the equation to support the translational equilibrium. And after that we should write down one more equation as the condition for the rotational equilibrium. The net torque equals to 0. And here you can see the torques that in sum, the algebraical sum of these torques of the all forces that are applied equals to 0. And the next, what should be said? What do we mean under the algebraical sum? We should pay in attention that force tends to rotate the rigid body, the lever, into one of two possible directions, clockwise or anti-clockwise. So that is why the two opposite signs, plus or minus, are prescribed to the torque, dependent on the direction of the rotation. So, and this makes the sum of the torques of the all forces to be algebraical sum. And now you can see what is the force that should be developed by the biceps. It is of 100 newtons. And look, it is greater than the external load. This biceps force should balance. So that is why we can say that it is the disadvantage. It is not mechanical advantage. The human body doesn't obtain advantage when the human, the people keep something heavy at their hands. The forearm is for another purpose. The forearm and the upper arm gives the possibility of the opportunity of the human body to move arm and hand much faster than biceps is moving when it is contracting. So that is why this lever we should name as the velocity lever, meaning that this structure of the skeleton, upper arm, gives the advantage in velocity for the human's body. So, and one more problem should be mentioned. It is the mechanical subjection of the structures inside mechanical subjection of the internal structures of the human body. Look here, the lowest part, the lumbar sacral region of the vertebral column, is that here the normal backbone deviates most from the vertical. The sacrum is attached firmly to the pelvis, so has much more limited movement, whereas the lumbar vertebrae are connected to each other only through the discs. And when we consider this as standing position, what we can see? In normal posture, the lumbar sacral disc lies at the angle of about 40 degrees to the horizontal. This is called the lumbar lordosis. The weight of the body on this disc is about 60% of the total body weight. It is called superincumbent weight, the weight lying on. This will be balanced by the support force of the sacrum S. You can see that this 60% of the body weight is balanced by the sacrum force, support sacrum force. These forces can be resolved to give a compressive stress perpendicular to the disc and a shear stress twisting parallel to the bone surface. And you can see what is the compressive stress on the disc and what is the shear stress, how high enough these two are. What should be said? The long time compression leads to tiredness of the material. So, this is not exception, the tissue of the disc. And this disc can start to be weaker, and the back pain may be a problem for the person. And one more should be mentioned, that the shear is not is worse than the compression deformation for the tissue. The tissue withstands much better to the compression than to shear stress. And look, summary of today's lecture is these. Physical models are correctly used to quantify objective description of the mechanical movement of skeletal muscles and bone structures of the human skeleton. evidence-based parameters of the functional state of skeletal muscles reflect the dynamometry physical method diagnosis. And one more, the body's tissues are subjected to various mechanical deformations. The quantitative assessment of the mechanical properties of tissues by physical methods allow to establish criteria of risks of mechanical impact on the human body. So, and finally, this is the bibliography. This should be mentioned as the basic recommendation resource, and you can go through the internet, particularly through this site, and find extra information. Look, we were here without break, so consequently take this 10 minutes break that you should spend within the lecture at the end of the lecture. Thanks for your presence, and unfortunately there is no time to answer to your questions properly and to react to your writing. But actually, let me suggest you to be present here to listen to me. Because after lecture, with some groups, I meet directly and we can discuss the subject topic of the lecture, and other groups will meet tutors and discuss or ask the questions that won't be clear at the lecture. You can ask your tutor. So we finish. Thank everybody.